Okay, so now we will discuss the Banks Zach's fixed point. Um, Now, the Banks-Zach's fixed point is also a CFT defined at weak coupling, just like the Wilson-Fisher fixed point was. What that means is we can study it using Feynman diagrams. We can use all of the tools that we know from perturbation theory. So that's nice. Now, one difference compared to the Wilson-Fisher fixed point is that the Banks fixed point is actually a gauge theory. So now we'll be studying a gauge theory that is a conformal field theory. And remember that in Banks-Zach's we had a competition between the effect of the coupling having a dimension and interactions, and we balanced those two effects. So the interactions wanted to make the coupling weaker, and the fact that the coupling had a small negative length dimension wants to make the coupling larger. By balancing those two effects, we got the beta function to vanish. At the Banks-Zach's fixed point, we again balance two effects, but the two effects that we balance are screening and anti-screening of the quantum vacuum. And screening and anti-screening will actually explain why the coupling grows or dies as we integrate our modes, so as we do our RG flow. Um, in 4 dimensions, the electric charge and the QCD coupling, these are all dimensionless. So again, the complete effect comes from interactions. So now we'll be discussing the effect of interactions when we discuss screening and anti-screening of the vacuum. So first of all, let's come to discuss screening. So this is screening by the quantum vacuum. So screening. So what's the physics here? The perfect theory to study this in is quantum electrodynamics. So I'll imagine that we're studying things in QED, but any charged matter will screen. So for example, the quarks in QCD will tend to screen the color charge. Okay, so let's put down the ideas that we need. So we know we have got many different modes in QFT. And since Wilson, how have we always thought about things? Well, we've thought about things according to energy scale. So we've got some modes like this, which are very high energy modes. And these high energy modes have a small wavelength that I'll denote by lambda. We also have modes which are low energy modes. Okay, and everything in between, of course, low energy modes. And these have got a very big wavelength. And what are you doing when you do RG? Well, so what does RG do? Let's just put it over here. RG eliminates um, the small wavelength modes. And what it does is it produces an effective theory, for the low energy modes, or equivalently for the big wavelength modes. So the effect of the small wavelength modes that you're integrating out is to produce an effective theory for the big wavelength modes, and in particular, the charge of this effective theory will be different to the charge that you started with. And this is why all of the couplings run. Another point about this effective theory, so the effective theory has a short distance cutoff. So the effective theory has a short distance cutoff. And what we mean by this, you've integrated out everything above a scale, let's say m. And that means that the biggest wave, the smallest wavelength that you've got, so all this out of all of the modes that you've kept, the smallest wavelength would just be 1 over m. Okay, what have I got in mind here? Well, I am thinking about de Broglie's wavelength. So what did de Broglie tell us? Lambda is equal to p, what, h over p. So If you have very big momentum, very big scale, you've got very small wavelengths. We've integrated out all of the modes with some energy above some scale, which now means the modes that are left, they all have wavelengths which are longer than some scale. So if, for example, you wanted to look at a point charge, so let's say there was some point charge with a charge Q, you wouldn't be able to resolve that point charge. Instead, you'd see it as a sphere, and the diameter of the sphere would be set by 1 over m. Okay, so you would no longer resolve point charges, you'd only resolve these spheres. So that's the first idea. When we look at these point charges, we're going to see them as little spheres just because we're working in the effective theory. The next thing to take into account is that the quantum vacuum is not empty. So the kinds of processes that you've got, if you've got a photon propagating along, it can pair create and it produces an electron and a positron pairs. There's an electron and there's a positron. Let me just draw it like this. And there's a positron. Okay. And if you want to think about this in terms of what you studied in classical electromagnetism, you should think about this as something like a dipole. So our quantum vacuum is full of these little dipoles that are popping in and out of the vacuum. And when we have a positive charge sitting there, that positive charge will polarize the vacuum in exactly the same way that an electric field polarizes a dielectric. So now I want to remind you of some of the things that you would have done when you learnt about electric fields polarizing dielectrics. So if we have some source of our electric field sitting here, we could have many dipoles, and what will happen is the dipoles will tend to align with the electric field. So we'll have all of these minus positive pairs, and they all align with the electric field. So that's the physics of just polarization of any medium. And now let's combine this with the fact that, in fact, we can't exactly resolve this charge Q. We only see the sphere because we're in the effective theory. We would have dipoles inside, dipoles outside, dipoles all over the place, just from the quantum vacuum, these E minus E plus pairs popping out of anywhere. And they will all be polarized by this charge. Now, if we want to work out the electric field of this point charge, then I think that you know this theorem. This is a spherically symmetric distribution, at least on average. So to write down what electric field do we expect? Well, it would be the electric field of a point charge with all of the charge inside that green sphere concentrated at the center of the sphere. So what would the charge inside the sphere be? Well, of course, we've got the charge Q. That's there. And if you've got a dipole that sits entirely inside the sphere, you'll add the minus and the plus of the dipole, so there's no contribution. For dipoles sitting entirely outside of the sphere, of course, they also don't contribute. But what's interesting is those dipoles that are cut by the sphere. Because the dipoles that are cut by the sphere, you add the negative charge, but not the positive charge. So what the polarization effect tends to do, it tends to decrease the charge. So clearly here you can see polarization decreases the charge Q. So if we think about how does our coupling run, well, let's draw an axis over here. Oh, why does the iPad do this? Let's draw an axis over here. Now we'll have another axis over here. On this axis, we could put our effective charge. Let me just call it Q effective. So that's the charge that we'd actually observe. Here we would call P over M. And remember that at each point here we've eliminated all of the modes above some scale. So here we're talking about the charges appearing as a sphere that's, quite small. But by the time we flowed over here, well, by now we've eliminated many, many more modes. So now we're talking about a sphere that's much bigger. So this bigger sphere cuts many more dipoles than that little sphere. So at this low energy, the charge is going to be lower than it was at the high energy. And what we see is, okay, let's maybe draw it in black. What we see is the charge gets smaller and smaller and smaller as we flow to low energies. So what are interactions doing? They're tending to decrease this coupling. The coupling is dimensionless. So we would say that the electric charge is marginally irrelevant. And this is due to interactions, due to polarization of the quantum vacuum. So this is what screening does. Screening tends to make charges irrelevant, tends to decrease charges. What I want to discuss next is the case of quantum chromodynamics, okay, QCD. And in QCD, we will see that we can have anti-screening. And what anti-screening tends to do, it tends to take the coupling and make it increase at low energies. So this is an effect called anti-screening. So anti-screening of the quantum vacuum. And that's what we will discuss next.